move on to chapter 7 today. So when you have salt, and if you put this guy in the water, this water turn into either acidic or basic or still neutral. Does this make a solution acidic or basic or neutral? Basic. Why? You're right.
And then the strong base.
Yeah. So
Base.
Na,
HCl would be a weak acid.
Na is linked to strong base. Cyanide linked to weak acid. So strong one always win. So this will be basic. That is kind of shortcut answer to this. More complete answer will be if you put this guy in the water, NaCN will completely dissociate like this. That's step one. And the second step, this guy with water, no reaction because this guy is from strong completely dissociate. That means there's no more reaction. It just stay as separate species. Cyanide, by the way, will react to the water, double arrow, and then producing hydroxide. So because of this reaction, solution will be basic. So sometimes they may ask you write all those reasoning behind of why this will be basic. Then you're going to write all of them. But in other cases, multiple choice. If they ask just X to basic, which one is X basic? Take shortcut, like we said. This is from strong stuff. This is weak stuff. So that will be just basic. It's all lucky. So then, this guy, sodium chloride is sodium from strong stuff, strong base. Cl is from strong acid. If both are strong, they just cancel each other. It will be neutral. So if you put NaC in the water, it will be neutral. What about you have ammonium cyanide? So ammonium cyanide, this one is from ammonia, this one from HCN. So both are weak. How do you determine it will be acidic or basic? Well, it goes by, the shortcut is again, if this is basic, what is KB? What is Ka, right? KB of ammonia is this, Ka of HCN is this. Relatively, this one is a bigger number, larger number than this guy, which means it will be basic. Overall, it will be basic. Why? This guy, ammonia has other stronger basic property compared to weak acid. So that's a shortcut. How do you find the pH of salt? Well, first of all, is it acidic or basic? If you put this one in the solution, it will be basic. Yeah, because this is strong stuff, this is weak stuff. It's basic. So in the water, cation dissociate as K plus and Cn minus cyanide. And then we know this will do no reaction in the water, so you have to write anything. But if sometimes you may have to explicitly write there's no reaction. So cyanide in water will reach the equilibrium. To find the pH, we need to know H plus or OH minus. And then we have OH minus right there. Initial concentration of that guy is 0.500. Do I use KA or KB? KB? KB. KB is x squared, and then x is hydroxide, and 0.500 minus x. So that will be equivalent to x squared, approximately this. Now KB value of HCN is not available in the table, so you're going to have to find out using the relation of that divided by KA of HCN. And then HCN is this, so 10 to the 14 divided by that number. So what's that? 10 to the 14 divided by 5.8. 0.00007. So my x, which means hydroxide, is now inside square root 0.500 times that guy 0.0000174. So I have this times 25 inside of square root. So that will be 0.002936. We have 3 sig field, so something like that. POH is negative log of this number. Negative log of that number is 2.5. Wait a minute, do we have 3 sig field? We cannot have 3 sig field because there's a 2 sig field here. There will be 2 sig field. So although this is 3 sig, we have 2 sig field. So right here, because 2 sig field, we're gonna have 3 decimal and 2 decimal. Okay, that's a pH. So then pH is 14 minus this number. Make it 11. 7.
Can I ask a clarifying question on that?
Yeah.
So in last semester in Chem 1, they told us not to use constants like Ka and Kb to determine sig figs. Is that different in this class?
So actually, whatever we measure, there will be sig fig. So who was the instructor at the time?
Lipinski?
Okay. So this is measured number. Somebody did experiment.
Okay.
So
Okay.
there's only 2 sig fig.
Okay, perfect. Thank you.
I mean, it may be having okay in that class.
Okay,
But
no,
here-
that's good to know. Thank you.
Any number that are not exact, there's a sig fig there. Lyral speed is a constant, 3.00 something, 10 to the 8. This is very universal constant in the universe. Still, there's like a certain sig fig. Whatever you measure, there's a sig fig. And so why don't you try this guy yourself? here. Does you want to get the same number? Okay. Why don't you try number 3 then? Number 3 doesn't need any calculation, right? It doesn't need any calculation. Can anybody explain why?
That's a strong base or strong acid, so she's neutralizing it. So it'll just be a neutral pH.
Very good. So this is from strong stuff. K is linked to strong base KOH. Br is linked to strong acid. So then this will be neutral. When you dissolve in the water, it will be neutral. So pH is 7. Okay. When you mix strong acid with strong base, they neutralize. They just cancel each other. We call that as a neutralization reaction. Especially when you have strong acid and strong base, then you get the water from H plus OH. They make water. Remaining part of negative ion make it salt. That is also true for weak acid and strong base. So strong base means it has hydroxide. Right? Any strong base, A strong base always have hydroxide. And then this is weak acid. So weak acid has hydrogen, strong base has hydroxide. So they will make water. Okay? And then the rest of them will make salt. But this will be exception. When weak base meets strong acid, weak base do not have hydroxide. Right? Ammonia is weak base. It does not have hydroxide, so there's no way to make H plus OH into water. So this is the case. Neutralization do not produce water. There's no water in it. Okay? It will just make salt. So sometimes they may give you a trick question. What is produced when you in neutralization reaction between acid and base? And then in multiple choice, there might be water. Water is not an answer because it's not like you're gonna have water all the time. So it's true for some time. This will be exception. But you do get salt no matter what. If you neutralize between acid and base, you always have salt. But water is not the case all the time. So that is from the chapter 16. We just finished the review of CHEM 1. So what we just reviewed in chapter 16 is very important to understand chapter 17. Okay. So you need to be very comfortable with chapter 16. Chapter 17 is more challenging. If you have hard time on the chapter 16, 17 will be more challenging. So in chapter 17, we just learned basically 4 things. Common ion effect, that's one thing. Another is buffer. And titration, solubility. Those are 4 main topics you're gonna learn in chapter 7. today, let's start with common ion effect. What's the common ion effect? Anybody? What's the common ion effect?
That's a good question.
This is actually just what is common ion effect? Do you know Le Chatelier's principle? Le Chatelier is a French name. What is Le Chatelier's principle?
Shifting the equilibrium on one side of the reaction.
You have understood what Le Chatelier's principle. So Le Chatelier's principle is, let's say, so this is example of weak acid. It could be any other reactant. When you have double arrow, which means there will be equilibrium between weak acid and there, the broken part. Okay, that's equilibrium. So if you have pure water and put acetic acid, there will be equilibrium between these guys. But what if water itself is not pure water? Let's say you used the water, but that water was actually acid rain. It has acid, a little bit of acid already. Or you put this guy first, and then later you add extra salt, like sodium acetate. Then in this water we already have CH3COOH, a lot of them, and a little bit of H plus because it dissociates a little bit, and the acetate a little bit. That's from equilibrium of that guy. But if you add extra salt made of sodium and that guy, then you are adding a little more of sodium and also acetate. So now this guy is added to this equilibrium, which means it disturbs equilibrium. Le Chatelier's principle says chemical system, once they settle at equilibrium, they do not want any change. It's like a human. Once you settle down in a certain life, you do not want too much change in your life. Okay? Because as long as it's good, you don't want to change it. So if you add extra this amount, this system try to oppose the change. So instead of having a lot more of that guy, you can shift this direction, so reduce that change. Okay, chemical system opposed to certain change. So when you add more of this guy, you can shift this direction, removing some of that. That means you make a little more of reactant. That's what we call Le Chatelier principle. Okay. Common ion effect is coming from that principle. When you have acid and then you put extra salt may have common ion. In this case, acetate. Acetate is in extra salt and at the same time in the original reactant. The common ion shift to equilibrium, in this case to the left. So acetate is common ion in this case, and the equilibrium will shift to the left. Then as a result, weak acid actually dissociates a little bit because it's weak. But when you add common ion like acetate, that dissociation will be even less because you can shift to left. Only so less amount will be dissociated now with this common ion. So adding common ion increase or decrease of ionization? Decrease, because equilibrium shift, push back to reactant. That decrease ionization effect. Then does that increase pH? Lower or raise? Does pH goes up or it goes down?
Raise.
Because if you shift this way, you're gonna have less hydrogen ion. Less hydrogen ion is more basic. The pH will go up. Okay? So when you put this salt, ammonium chloride, in the water, is that basic or acidic? This is a review.
Acidic.
This guy make it acidic, right? NH4, Cl, completely dissociate. And it will make it acidic due to ammonium ion. That's from this salt. But in your solution, if you add ammonia, then right, so this. So when we have only salt without this guy, this is the reaction you're gonna write down. So first step is dissociation, and the second step this guy hydrolyze. Okay? If you have only this one kind, this is the reaction you're gonna write down. But when you are given two compounds, now this guy itself acts as base, and the salt will provide extra ammonium ion. So these are the two you're gonna write down. This guy and that guy. Okay. So this will be common ion in both reactions. And then this is equilibrium. When you add this guy over here, because that increase ammonium ion, it disturb equilibrium to backward. Okay, equilibrium will shift the left. Okay, these are the two reactions you're gonna have to write. So to answer this, those two reactions. Now let's do something here. Okay. So this is what you did already. But why don't you do again? If you have acetic acid that dissociate in the water, A is acetate, CH. I'm going to write that. Acetic acid, 0.10 molar percent initially. So 0, and equilibrium. This Ka is x square. you have common ion, so that was 1. If you have common ion, setup is a little bit different. Initially we have 0.10, so same situation. Oh, at the same time we have a 0.10 molar concentration of sodium acetate, which means we have this on that side, so 0. Change, you will lose X amount, add X amount, at equilibrium, 0.10 minus X, X, 0.10 plus X. This is common ion effect, okay? With the common ion, that was just X. In this case, it will be added to the X, that number. So, to compare the left side, X times but we assume X will be very small. It is very small compared to initial constant here, right? And then it just considered very good approximation. Now I have a question. We assume the X will be small compared to 0.0. Now common ion effect will change that. But how does it change? We said in this case, if you have common ion, like acetate, if you put more heat, more of acetate, it could shift to left or right? Left. Left means there's more dissociation or less dissociation? Less dissociation. That means X will be even smaller than before, right? If you could use approximation, X will be small compared to that. Now this will be even more so. So you can really safely say X can be ignored. So in the bottom I have 0.10. On the top this one also go away. So 0.10 and I have X. So this cancel. It will be X. And X was concentration of proton. Of course, at the same time, this guy. Therefore, and Ka was given as 1.8. 1.8 5 is. So because we know H, we can find the pH equal negative log H plus. But that is same as this number, negative log 1.8 minus negative plus. So right here, 4.74. On this side, I didn't do calculation. Let's say we're gonna have that number. This is confirmation of what we just said. When you have common ion, there will be less dissociation. There's less dissociation, it's less acidic. Because less acidic, there will be a higher pH. You can see this is like about 100 times less dissociation there, right? Common ion cause about 100 times less dissociation of pH. Any questions so far? will happen if you have a solution of HF? So in the solution, you have HF that dissolve and dissociate like this. Most of them just stay as we get only a little bit of that dissociation. Now you are adding extra Kf. So that will also dissociate like K plus F minus. So we see common ion, right? This acid has fluoride. This salt provides another fluoride. So you are adding more of this guy. So what happened? Does the equilibrium shift to left or right? Left. This is not correct. You are adding common ion to product side. You should shift to the left, not right. Does that increase pH or decrease pH? Increase pH. Why? Because there's less dissociation. So increase pH. Increase pH. Does it decrease Ka value because there's less dissociation?
I figured it increases because the denominator is smaller than
the expression for Ka is H product over reactant. So if you shift this way, that means you have more of this guy, less of that guy, right? Does it make it decrease? What do you think? So if you shift this way, it increase this guy, decrease that guy. Does it make this number smaller?
Yes.
That was actually a trick question. K doesn't change. No change there. Why? Ka is equilibrium constant. Equilibrium constant doesn't change when you change the concentration. Okay? So then how that makes sense? Well, we said adding more of this guy make it can shift this way. So obviously this guy increased, that's true. This guy decreased, that's also true. But what about fluoride? Well, you can shift this way, original fluoride amount will be decreasing. But you added more extra fluoride. So overall fluoride actually increased. And then increase to the amount, everything is balanced, and actually K does not change. Okay. So when you add or remove certain component, it doesn't change Ka value. That's equal constant. Ka will change any equal constant, not only Ka, Kb, Kp, Kc, Ksp, whatever K, those are all equal constant. That doesn't change unless you change temperature. Okay? You change pressure, volume, concentration. This guy never change unless you change temperature. Right. So does fluoride content increase or decrease? You can shift this way. Increase? Yeah, they increase. We actually did that. Original amount will decrease, but we add more. So overall concentration of fluoride actually increase. All this effect is due to common ion effect. So everything here we can say common ion. In this case, fluoride. This is all common ion effect. Common ion effect. everything what happened here is correct. Let's say I have a weak acid, nitrous acid, and dissolve in the water. So this guy will dissolve in water, H plus and O2 minus, nitrous ion. Now, if we put this guy instead of pure water, if we put in existing solution, when this guy ionize less, in which situation? So if you put into pure water, it will dissociate like that. But water itself includes this guy already in it. And then you are adding the acid to in this solution. In which case this guy dissociates less. KNO2. See? Yes. Because KO2 will provide common ion, nitrous ion, like that. So that will make this equilibrium shift to the left. Is there any other case? No. K is not common ion, so that's it. Very good. In previous slide, our common ion was like other ion than proton here, but sometimes proton itself could be common ion. Okay. In this slide, so weak acid acids would dissociate like that and reach equilibrium. What if we add extra strong acid to this equilibrium? Well, strong acid always 100% dissociate, giving proton and chloride. So to this, we are adding more of this guy, right? More of that guy. This guy doesn't do anything because this is nothing to do with this equilibrium. It has no effect. But this proton from strong acid will disturb equilibrium and equilibrium shift left again. So in this reaction, proton is common ion. And again, because you add in the product side, equilibrium shift back to the reactant side, which means to left. So adding that common ion half proton, does it increase ionization or decrease ionization? Decrease. Why? If you shift to the left, that means there will be less dissociation of this guy. Less dissociation. So that decrease. Because it decreases dissociation, does it increase pH or decrease pH?
Decrease.
Decreases pH. Why is that?
pH up, acidity down.
So it is shifting to the back side, so it decreases original hydrogen concentration. But we actually added this guy through here. So overall, actually it increased hydrogen concentration, which means it lower pH. Okay?
Can you explain why one more time?
Yeah. So that we actually have equilibrium here, but we are adding common ion through strong acid, but this time common ion is proton. So you are adding certain product, equilibrium shift to the left. So obviously there will be less dissociation. Less dissociation means this guy itself will produce less proton. But proton is not only coming from this guy, we are adding proton from outside the source. And then when you compare weak acid and strong acid, the amount provided the proton amount provided by this guy is nothing. This weak X provides a little bit of a proton, while strong X provides a lot. So whatever dissociate from this guy is nothing compared to what you added here.
That makes
That's
more
why
sense.
it will increase proton concentration
Thank
and
you.
lower pH. Why don't you try this?
이게 same number?
What is a buffer? Buffer.
Maintains the pH.
Yes. Buffer is a solution that maintains pH relatively constant. If our body is like not a buffer system and it has lots of water and not buffer system, then a little bit of acid will change our pH drastically. Either a little bit of acid or base. If you, let's say you just drink some Coke, now your pH will change a lot. But fortunately, our body system is a buffer system, so if you drink Coke, you have no problem. Well, Coke isn't that much acidic, but it's acidic. So, buffer system is whether in solution when you add either acid or base, this system has certain compound that can neutralize either acid or base. So buffer system should have those two pairs. Normally, we have certain weak acid and its conjugate base. Okay? This guy will dissociate as in water, acetate, and proton. So we make buffer system by mixing original acid and its conjugate base together. You use salt that include conjugate base, then this will be your buffer. Okay? But we can use only weak acid. We are not using like a strong acid like H2SO4 and its conjugate, which is HSO4 Na. This doesn't make it buffer. Okay? It should be always weak acid or weak base, like ammonia, and its conjugate base or conjugate acid. So ammonia and ammonium chloride, that will also make buffer, but it shouldn't be strong acid and its conjugate. Okay? Now let's get so let's see how that buffer works. So in your, actually we can do that later. So now, in which case you will make a buffer then? So condition is you have to have either weak acid or weak base, and at the same time conjugate pair of that. So which one is a buffer system? It's A is buffer. Yeah, because you have weak acid and it's conjugate base. So it's a buffer. Is B buffer? No? What's the difference between A and B? Everything is same except now this number is equal. It's not equal. When we define the buffer, we didn't say anything about the number, right? So this is a buffer. Because it has weak acid and it's conjugate base. It will be a buffer. It doesn't have to be same number. It doesn't have to be equal amount. It doesn't matter. You see buffer? You have weak base and it's conjugate acid, right? So it's a buffer. What about D? D isn't buffer. So what if you want to make what will change here to make buffer? What should you put here instead of that guy? Because we have this one already in a lot of cases. Let's delete this guy. HF. HF. So if you use HF, that should be exit. This is a conjugate base. So if you have HF, this will become buffer. Okay? Is this buffer? Yes? Because it has accident base.
Strong acid, strong.
So it's a buffer. The buffer is made of only weak stuff. Okay? Strong guy do not make a buffer. So this is not a buffer system. No. Now, if we have somehow make a buffer system, that's when we use Henderson-Hasselbalch equation. That would be very convenient equation when you deal with buffer system. Okay? So let's see how that equation is derived. You have weak acid in water and dissociate into conjugate ion and proton. So this is your Ka value. Right? Actually dissociate into proton and conjugate base. Now we just rearrange this on that side, and then this guy just go the other side. So it will look like this. Okay? So it's just rearrangement of equilibrium constant. And then take logarithm, negative logarithm of both sides. Okay? Negative logarithm of proton or hydrogen ion. Now, I assume you are familiar with logarithm property. If you have a logarithm, multiplication of two guys will turn into log A plus log B, right? That's one of the property from algebra. Therefore, multiplication of this guy will just become addition. Logarithm Ka, logarithm of this guy. There's a negative because we just define negative logarithm over there. So now negative log is what we call P. So this is nothing but pH. This guy also negative logarithm P, so it's pKa. Now we have removed negative sign, but another property of logarithm is if we have a logarithm like this, that will be I can rewrite logarithm of negative power. Whatever power you have here can come in front of logarithm. Okay? This is true not only for one, for any number. If you have a logarithm A of exponent B, that is same as B log A. Okay? Because of that, negative can go over here as logarithm negative exponent HA A minus. That will make it reverse up and down. So we give this equation fancy name like Henderson-Hasselbalch equation, but actually that is actually nothing but it's the same as equilibrium constant. Right? It's the same thing. It's just mathematical manipulation, just rearranged and then take logarithm. That's it. But still, we just give this guy tribute, these two guys. Okay? Why? This is a very convenient equation when you deal with buffer system. That's why. And I encourage you memorize this. It's not must. If you actually you can start from this because this is mathematically almost same thing. You can start using that to solve a problem. But if you use this, it's quicker. So I encourage you memorizing. But if you do not want to memorize it, that'll be fine. You can use that. It just takes longer. So why don't we do a little practice using that equation here? We have a buffer system made by axis here and conjugate base, right? So because compound includes one of the axis, conjugate base, so we can call that as buffer system. Because it's a buffer system, they say calculate pH value, where pH is equal to pKa plus log x down here, base, conjugate base up there. And the Ka value is given right here. So pK value is negative logarithm of this number plus logarithm of concept of HA, which means exit 0.250, and then conjugate base concentration 0.10. So answer for that question is just -4 1.8 4 plus another log 21 divided by 0.5 3 3 4 6. So 2 sig fig 3.35. Now if you use this equation, it's a lot easier. But let's go back to our Ka expression and do that again. Okay? So although I encourage you memorize this, let's say somehow you forgot that, but you still know Ka is H plus A minus HA. Okay. And we have HA, H plus, A minus. And initially, we got that much X, 0.250. And conjugate base as 0.100. So at equilibrium, therefore Ka value for that guy is 1.8. And here X as approximation, you have X 0.50. So X, my X, H plus is 1.8 times 0.50 and 1.00. That H pH will be relative logarithm of this number. So you should get same result. So it's not bad to use this Ka expression. You can just set it in icebox, and then still you're going to end up finding the same number. So if you do not want to memorize any extra equation, then it will be okay to use this. But sometimes when you do lots of calculation, memorizing one formula will make it a lot simpler. Okay. Do you have any questions? This is last slide for today.
You're gonna go over the quiz now?
Hmm?
You're gonna go over the quiz now?
Do you have any questions about quiz? So let's see.
I didn't see these questions, like number one,
This one?
We had that on the other quiz, basically,
You mean this guy?
too, yeah, and I couldn't.
Okay,
I'm not
alright,
ready for either one, I don't think.
It's base ionization, so if that work at base, what base do is accept proton. If it accept proton, it will make a hydroxide ion. So KB expression is product over reactant. Not including water. That will be KB expression. By the way, hydrogen proton will be added to nitrogen. That's why I have increased the hydrogen number here, not increasing just like that. I didn't do this.
I don't know, I must not have,
Yeah. Hydrogen will always add to nitrogen side.
I guess I didn't see that answer on there.
Oh, you didn't see this guy in the.
I'm probably wrong, I'm not very good at this, but I don't know. Seems pretty simple, I keep screwing it up, I guess.
Do you have any questions about the other quiz? Okay, if not, then we're gonna see next time. And also,
Yeah, I got the pH wrong too, I couldn't figure that out either. I was just doing them before this, and I'm fine with it, so I don't know.
yeah, I'll be open the lunchtime every day, so I think it's pretty more.
Yeah.
And then expect that you're gonna have a quiz like 5,